So the next thing we did in regression, and we are going to repeat here again, is to verify the assumption visually. So what are the assumptions we made in this design? First, we made that the errors are statistically independent. This is always common assumption. All right? That the errors are additive, and this is very important assumption because we just put the plus E. Errors are normally distributed because we are using T distribution for that reason, right? Errors have a constant and standard deviation, so they are not varying. And the effects of the factors are additive, that A and B add, XA plus XB, right? And if you make all these 5 assumptions, then your conclusion is that the observations are independent and normally distributed with a constant variance. And all of these formulas that we did, the confidence and statistics and this and that, all are based upon these 5. So we have to verify these 5. So how do we verify these 5? So let me ask you, without going too further, maybe it is in the next slide next, but basically let's do, how would you verify that the errors are statistically independent or they are not dependent? Now the errors are additive, kind of difficult to verify right now. Errors are normally distributed, we know. How to do normal distribution? That's the simplest one. What is that? How do you verify normal distribution? Yeah, QQ plot. Errors have a constant standard deviation. Again, we will just see whether they are, they look like constant. And the effects of factors are additive. That is difficult to verify. So anyway, so how do we verify independent errors? Scatter plots of residuals versus the predicted response, and then we look at the magnitude. If the magnitude is small, we are happy. If they are large, then we worry about the trends. We can also plot the residuals as a function of the experiment number. We can see the trends. Normally distributed, quantile. Constant standard deviation, we again look at the, how the spread is. So this is what we do for this study. So for the memory cache study, you did, these are the 12 errors, and this is the predicted response, and this is the residual. So the key thing is to look at the y-axis. It goes up from -5 to +5, but the x-axis goes up to 80. All right. So if you don't care for 10%, then this is a small error. Okay. QQ plot shows good enough, so that's good. However, so this is all about this model. However, believe it or not, while doing these things, while teaching these things, we discovered some problems with these models. And so some of the students who did the project just like you, and they came up with some conclusions which were not valid. So they said, sir, this doesn't look like the right thing. What is wrong here? And we discovered what we call multiplicative models. Now, it's not that we discovered in the sense that people didn't know before. Yes, people knew about the multiplicative models before, but this is all in the agricultural field and the medical field. In computer science, we didn't. And so this is an important thing to notice now. So the thing is, what is a multiplicative model? Here we assume that everything adds up. This is not a valid model if the effects do not add up. For example, execution time of the workload. Remember in the exam you had this workload thing with things multiplied? Well, there are lots of such things in the computer science which multiply. So the processor speed times the workload size, they multiply. Alright? But if you take a log, then they add. So for example, execution time is, now let me be sure that this is correct formula. Execution time is Yij is equal to Vi. Vi is the instructions per second. No, this is not the correct formula, right? There has to be a division here. This has to be Wj upon Vi. So this is seconds is equal to instructions divided by instructions per second. So this would be, not a big deal. But basically this would be Wj divided by Vi. It's still multiplicative if you really want to call it, it's multiplying. So you take a log of it and it becomes additive. And so that would be the model. So for this kind of thing, you know that they don't add up. If you are measuring execution time and you have a processor and you have workload, you know that the workload and the process don't add up. So before you do that, you have to take a log, and now they will add up. Yeah, right. The thing is, this is where the system knowledge comes in. So what will happen is, if you do this thing, and we will do this in both ways, additive, you will come out with some really crazy conclusions, and you'll say, sir, this doesn't look like right, okay? That's when you start looking at, is the model really good, right? And then the system people will say, well, I think this is, this thing has this effect, and then you will say, oh, yeah, if you come up with something like multiplication, then you have a multiplicative model, and then all the inconsistencies will be gone. So so the thing is, it could be another transformation. So just like we talked about other transformations in regression, those transformations will come up too in a minute. But first, let's do the multiplicative model. So once you get the multiplicative model, then you take the anti-log, and you get the effects of, and basically and then you start talking about the geometric mean, because your Q naught is the effect before the anti-log. After the anti-log, things just, was adding with multiplying. All right, so let's take an example of this. So we measured the execution time of 4 workloads. So these are the work, so let's see, of 2 workloads in 2 processors, okay? 2 workloads and 2 processors. And so the execution time was that, these are the combinations. And if you do the mean as usual from before, you will come up with something. But before we do something here, one thing you have to do, and this is another art form now you will learn, and I probably have already learned before because we have talked about this before. You look at the numbers you are adding to get these means. So you got the mean of 2655. It is a mean of these 12 numbers. Right? What are these numbers? They are going from 0.01 to 85. Alright, you are adding numbers which are very different. The range is 10⁴. Right? When you find yourself doing such things, then you know that you are doing it wrong. You cannot be taking mean of things which are so wide. And that is the first thing. Y max upon Y min is 12,534, and therefore when you have such a thing, then you have to see what can I do to reduce this range. And that is one way you will find out that maybe I should try multiplication, because maybe I should try log here. So basically, this is the giveaway, that you don't want to add up numbers which are so different. And if you did use that model, this is what your test will fail, because now you do the predicted response versus residual. The scale here is 160, the scale here is 50 to minus 50, 100. Right? So the errors don't go down. Alright? So, and the error is 0 here, and then this is like that. It doesn't look like constant error, standard deviation either. So it fails that test as well. And when you do the QQ plot, doesn't look like a straight line to us. It looks like totally different straight line. And so on. So you will find lots of inconsistencies, and one of them will nudge you towards the multiplication. So basically we take the log, and once we take the log, we do the analysis, and then we plot. Okay? So now when we plot, the range here is 2 to minus 2 predicted response, and here is minus 0.02 to 0.02, 1/10. So the errors are less than 10% right there. Now look at the spread. What do you think about the spread? Is it constant? No. Alright, so that's that's a concern, that the spread is not constant. The errors do not have a constant standard deviation. Alright? The only thing against that one could argue is that, well, they are less than 10%, so I don't care. Alright? But that's an art. That's the thing that people can argue about. Alright, I will leave it there. The straight line part is same thing. The straight line is almost there, except for this one point which one could argue whether it is there or not there. straight line, right? But this is much better than the other model, that is for sure. So how do we interpret these results? So these results basically say that the model is log y is a linear function of these things, and therefore y is 10 raised to q naught plus 10 raised to qa xa and so on and so forth. And if you put the values in of q naught, qa, qb, qab, then we get this model, that the mean performance is 1.07. When you have xa, which could be the processor, then the performance goes up and down by 0.107, factor of 0.107. Because if it is plus 1, this will multiply, minus 1, this will divide. The workload also has the same effect. It goes up by 0.107 or goes down by 0.107, by a factor of 0.107. And the interaction, it turns out, has the same effect. This is just an example, okay? It turns out, I'm really surprised that they have the same value. No, I think there is a mistake here. This is a typo. 10 raised to 97 is okay, but 10 raised to 03, this should be some small number. You have to write down, find out. The last number is this, it is wrong. 10 raised to 0.03 is written right here. 10 raised to 0.03 is 1.07. Oh yeah, okay. So this is 1.07 and this is 0.107. By the way, this is really interesting, is that 1.07 has no effect almost. Okay, you multiply by 1 or divide by 1, who cares? But 0.107 has significant, is big, because if you multiply by 0.107, it goes 1/10 by factor of 10, or it goes by factor of 10, right? So that is what was confusing me for a minute. Alright, so this is 1.07 and this is 0.107. Okay, with that, so how we say? We say that the time for an average processor on an average benchmark is 1.07. On processor A1 is 9 times that of an average processor. On processor A2 it is 1/9 of an average processor. So the factor is 81 times. The two processors are different by a factor of 81. Benchmark B executes 81 times more instructions than B2, and the interaction is negligible. So this is a multiplicative model. And basically, in many of the problems that you are working on, you have to first think whether they are really additive or not before you really even try an additive model. So once we understand multiplicative model, then all of the things that we did for regression again apply, including the transformations. And so the transformations could be many. I think this transformation probably was discussed in regression. If not, we are going to discuss it here again. But we talked about how to find a function h given a function g which tells you the spread. All of those things apply here. A common transformation method which is used in experimental design is called Box-Cox family of transformation, where you raise y to the power a and divide by sum a z raised to a minus 1, and we don't know the value of a, so we estimate the value of a. And so this is all described in the book. I would let you read about it rather than going through here. So there are other transformations other than just log. Alright, so now that we understand that 2 raised to k R design and what we can do in terms of transformation, we can just extend that to 2 raised to k R. And k R simply means that we write 2 raised to k terms plus the error terms. Parameter estimation is as before using the sign table. You get the same SSYs, SSTs, you get the same effects, standard deviation, contrast, predictions, everything else is the same assumptions, and then you have the same visual tests. And this is an example. I really don't have to go through this example, but basically these, instead of 4 rows, now you have 8 rows, 3 factors A, B, C, A, B, B, C, and so on and so forth. You divide that and you get the percentage variation explained. So here is the result. A explains 14%, B explains 5%, C explains 75%. Again, you can see that which are the most important parameters and then you can calculate the confidence intervals to calculate which of them are significant. So let's see, did we do the significance? Here is the significance part. So you do the confidence interval, and this part is 0, everything else is non-zero. So the interactions are small and insignificant. Then the prediction the same way, you just have to repeat the same formulas for m experiments. And so now there is a case study. Now this is a case study for garbage collection. Everybody knows garbage collection? I think I asked you before too. Everybody knows garbage collection, right? Okay. This was probably an example I did it very first time when we were doing introduction to the course. So this is a case study. It has, so some people were designing some garbage collection algorithm, and so they had 4 factors: the workload, compiler, limbo list, and chunk size. Okay, probably limbo list is their invention. Okay, it doesn't matter what limbo list is or what it was, but limbo list is the thing that they want to try out, right? But that algorithm also has 2 parameters: chunk size. They could use 4K byte as the allocation and deallocation chunk for memory, or 16 kilobytes. Right, so those are really the 2 things, and these 2 things can affect the performance, so they put those there. 4 parameters, each of them at 2 levels. Right, so they have 2⁴ design. And they repeated each thing by 3 times, and these are real numbers, so these are not made up numbers. They repeated each thing three times, so they have these 16 times 3, 48 numbers. This is the mean. They did the table, sine table method, and this is the final result: percentage variation and confidence interval. So now let us see. The A effects explain 34%. We should not even write this number here because this is not really, I is not, so that one, ignore that number. 34% is A, D is 52%, and AD is 12%. Everything else is not important and not significant either. Now, see, the insignificant parts are only this. This is only 2 insignificant. Both of them, All right. So now, given that, really we have to concentrate on 3 things: A, D, and AD. All right. Now let's see what is A, D, and AD. A is the workload. D is the chunk size. Now, what about the people who designed the limbo list? It doesn't have an effect. So this is the thing, is that they really wanted to see that the C has the most effect. But C didn't have the most effect. It is the chunk size which had the most effect. So you could easily conclude that really, if you wanted to improve your memory interaction, memory performance, all you do is allocate whatever chunk it is telling you, small or big. And doesn't matter what algorithm you use. Alright, so the conclusion is most of the variation is explained by A, D, and AD. The variation due to experimental error is small, so that is one thing. Is several effects explain less than 0.05% of the variation. Only AD are significant. Alright, that's it. So just hold on to this thought a little bit more, because we are going to complicate things more a little bit. And I don't have to. No, but at this simple level, at least you understand that now you don't have to put too much effort on C or B. If I was given more time, I will probably do 5 levels for D and A, and then do maybe 3 levels for B and C, just to be sure that I didn't miss anything. Right? I could do 10 levels for A and maybe 10 levels for D, because D is the most impacted one, and maybe 5 levels for A and maybe 3 for B, so on and so forth. See what I mean? So first we find out what is the overall impact, and then we are not sure still, because we would have missed the middle someplace. right? This is 2 levels. So then we say, okay, like this one has the most impact. Now we want to see whether it is going like parabolic, or is it just going at the end, or linear. So we do on D more, right? So we spend our time where it matters. Again, let me repeat this thing. This experiment says that between the 2 ends of C there is no effect, no difference. Whether C is -1 or +1, there is no difference. All right. Now C in the middle could make a difference. Right? So if you really want to be sure, you will run another experiment with the middle. Now, if it's quite possible that there is no effect in the middle, but there is something like this, and then there is something else. What can you do? Systems don't generally behave that way. Systems generally behave, more like one directional, unimodal, but there could be, 15 modal systems. Who knows? So basically, what we do is, particularly in simulations, we run a simulation, we think we are done, but it turns out that the errors is either too small or too large. Let's say errors are too large. Then we sit down and do the calculation, and we say, okay, we need 10,000 more. We run it. So that, generally if it is too small, then we don't go back and do anything, But we verify that the errors are not too large. That brings us to the end of this chapter. All right, so let me finish this for today. Replications allow estimation of the measurement errors. That's the key part. Now with the errors, you can now do the confidence intervals, and for the predictions, for the parameters, for the contrast. And then we also learned the visual tests, and then we learned about the multiplicative models. All right, so there is a homework 18B, which is you just have to do 18. That's what I was missing. That in 18A we did not do the other things. So we are going to do percentage variation explained and conduct the visual test. So that will be complete homework.